Okay, so let us start from where we left in the last lecture. So, we were looking at substitutional kind of impurity. In substitutional impurity, as we said that one of the atoms has been replaced, A has been replaced by impurity B. Therefore, we have different kind of bond. So, initially what should have been AA bonds now has been replaced by AB bonds, and we said that this delta HF, the enthalpy of formation, can now be approximated by difference in this bonding energies. Now, let us we also consider the situation of ideal solution where HAA, that is the bond between AA, is same as the bond between AB and the bond between BB, and in that case as you can see that delta HF comes out to be approximately 0. So, we have a straight line here, and this is on the x axis what we have is the fraction of B impurities or B particles, and as you keep going this side is the pure B, and then you go from here it is like adding A impurity. So, this is delta HF, it comes out to 0, and this is the minus T delta S term which is which becomes equal to delta G. So, delta G equal to minus T delta S forms like this, and this will be minimum at x b equal to 0.5. Now, next thing that we said we will consider is the non-ideal solution. So, here what we have is that HAA is not equal to HAB, not equal to HBB. So, how would it look like? This is now our simple the way we have been drawing so far, which is so again we are taking the same axis, A, pure A over here, pure B over here, and we keep increasing, and on the y axis is the energy scale. So, what will happen? So, somewhere over here is the 0. So, when you have let us talk about the pure A. So, you are adding B impurity. So, there will be delta H. So, delta H when B is being inserted in as impurity in pure A. So, this is delta H, and simultaneously for this there will be a T delta S which will go something like this. On this side again we will have pure B and A is being put in as impurity. So, this will, so let me draw it in a more straight line, this is supposed to be straight line. So, this is delta H A going to B. So, here A is acting like impurity and B is the pure material, here B is the impurity and A is the pure material. So, here this will be something like this. So, this is the minus T delta S, and again to differentiate I will say B going in A, and here A going in B, and I should not put minus because it is already in the negative scale. So, this is how it would look like, and corresponding to that you will find x b, corresponding to this you will find x a. And remember this is since this is non-ideal solution, we have to again limit ourselves to very small concentration. So, this region that we are talking about are very small quantities. Whether we are talking over here or whether we are talking about here, and in between we do not know, we will need to have a phase diagram to understand what is going on over here. So, I have given a break mark over here. So, in between this you do not know what is going to happen, whether there is an intermetallic forming or something. So, there is gap of knowledge in here. Anyhow, like I said last time, you have to maintain a caution that when we are dealing with this solution defect as a solution, you have to remember that defect concentration has to be very small. So, although we have exaggerated here to draw the whole plot, and even here we are trying to show the both sides, but that ideally that is not the right thing. It is just to give you a better understanding on what it would mean when HA is equal to HAB and when HA is not equal to HAB. But otherwise we should not extend this information from beyond small quantities. Okay, so with that we will move on to another kind of the interstitial substitution sorry, we have already looked at substitutional, now we will look at interstitial. So, impurity of different kind which is interstitial. So, we saw some of the characteristics like it is easy to find a site because all the sites are available, it is easy to move because there are almost all vacancies everywhere, and the major problem here is the availability the size that is available here. And to understand this we will look at carbon in iron which is what we call as steel. Okay. So, most of you would already know that iron exists in two states, one is the ferrite, what is the structure BCC, and the other is the austenite which is the FCC, face centered cubic, and this is the body centered cubic, and this is at low temperature and this is found at higher temperature. Now, what is the percentage of space occupied in BCC or what is called as packing fraction? We know that packing fraction of BCC is equal to 0.68, and what is the packing fraction of FCC? It is equal to 0.74. So, what does this imply? That BCC is a more open structure, right, because it has more empty space. Now, if I give you, you would already be knowing that carbon sits in interstitial, the carbon in the FeC alloy, which is steel, primarily steel, carbon sits at interstitials. Then one would be inclined to say that since BCC is a more open structure and if carbon sits can go in both FCC and BCC, you would be inclined to say that carbon should prefer BCC and solid solubility, carbon solid solubility should be higher in BCC. This is something that you would expect given these information, that in FeC alloy carbon sits in interstitials, BCC has a packing fraction of 0.68 and FCC has a packing fraction of 0.74, and assuming that the approximate lattice parameter are similar, not different by very large magnitude. But the question is it true? So, we will see. To understand this, we need to understand that in these cubic structures you have two different kinds of voids, because now we are talking about interstitials. So, the atom which set are go to a particular void, and there are two different kinds of voids in cubic system. One is called tetrahedral and the other is called octahedral. Okay. So, now let us look at what do we mean by tetrahedral and octahedral. Tetrahedral means that you have 4 faces. So, it is like a pyramid which has, but a little different from pyramid. So, here you have atom, here you have atom, here you have atom, here you have atom, and inside this space there is sufficient space for one atom. Now, that will depend on the lattice parameter and where exactly this tetrahedral site we are talking about, that we will see in more detail in a moment. So, let me. So, this is a pyramid with 4 faces, 4 triangular faces, and we have some space in here where you can make a atom set. What is a octahedral? In octahedral you can assume it that it has 8 faces, not assume, basically it has 8 faces. So, it goes like so, here you have atom, here you have atom, here you have atom. Now, the way I am drawing, I am intentionally showing a much larger space than it is actually available, just to make you understand where this void is, because if I really draw it in the scale of the atoms, you would see it would appear that there is no space at all here. But to make you understand that there is a space here, I have drawn the atoms to be very small, and so there is a space in over here where your atom can sit. So, this is the octahedral void. Now, we will look at the two different systems, which is one is the first, let us look at FCC. So, now I have brought a model over here. So, this is not really FCC. Why it is not FCC? Because here the two atoms have been given different colors. It is showing that these are two different atoms, but let us assume that these are same atoms. Okay, I did not have the model where both of them were of same color. So, for now you will assume that yellow and red are same atom. So, this is the FCC. Now, this is how the FCC would look like. Now, where is the tetrahedral void in this? So, first let us look at the tetrahedral void. So, now where is the tetrahedral void? Remember, this is the same atom, this is same atom, all these are similar atom. So, now if you look at it carefully, this atom, this atom, this atom and this atom. Now, what do you see? Does it form a tetrahedral? These 4 together, all of them, remember, are same atom. Like I said, for the time being, forget the colors, assume that they are same atom. So, 1, 2, 3 and 4. So, 3 face center and 1 corner atom. Do you see a tetrahedral kind of structure? So, this is the tetrahedral void in FCC. So, now you are able to see that. Now, let us go to the other void in this, which is that octahedral void. So, to understand octahedral void, let us look at, so here is one missing atom over here. So, let us assume this tip of my finger is another atom. So, now look at 1 atom, 2 atom, 3 atom, 4 atom, 5 atom and 6 atoms. So, all the face centered atoms. So, this 6 atoms together, they make, what do you see? What is the kind of structure it is making? It is a square on this plane, and there is 1 atom on the top and 1 atom at the bottom, just around the center of the axis, and this would look very similar to what we have drawn over here. So, this is octahedral and this is thus octahedral in the FCC. So, now we have seen how the octahedral void looks like and how the tetrahedral void looks like, but there is still one more thing. Now, I have shown you this void over here in the octahedral void for the FCC. Now, this is not the only octahedral void over here. Assume that there is another atom, another cell over here. So, there will be face centered over here, there will be face centered atom over here, there will be face centered atom over here and there is face centered atom over here. These 4 atoms again form a plane square, and along the center axis you again see this atom and this atom. So, this again, this also forms a octahedral. So, in the FCC there is one octahedral at the very center of the cell and also at the edges of the, at the center of the edges, at center of each of the edges. So, we will draw it again over here, but this is to make you understand this is where the octahedral voids lie. So, there are 2 different places where octahedral void lies in the FCC. So, that is FCC. Now, let me just draw it over here so that you can remember it. So, this is our cell and I will draw the atoms light blue so that it does not get too crowded. So, these are the corner atoms, and now I will draw the, I am drawing a little different size. So, just again so that it does not get too crowded. So, now you can see the corner atoms and the face centered atoms, all of them being the same color. So, where did I showed you the tetrahedral? So, the tetrahedral was like, if you assume that this and this face center and this corner. So, this is one tetrahedral in here. Now, you can imagine how many tetrahedral would be there. There should be 8. So, around each corner is associated with 1, and that particular tetrahedral site remains inside the cell. So, there is 1 over here, there is 1 over here, 1 over here, and similarly on the bottom side. So, there are 8 tetrahedral. Now, let us go back to the octahedral. So, I will have to draw this again. So, let me draw the corner atoms. And by now, you should be in a position to identify where the first octahedron is. So, where is the first octahedron? It is in the very center. So, I will join these. So, this is the plane and these are the 2 atoms. Okay, I have drawn, I am missing one atom in the bottom. So, I hope you are able to see, this is the plane. So, I will draw it with solid line now, and these are the 2 atoms on top and bottom. So, inside this is the first octahedral void. And where else did we say that there are octahedral voids? There are octahedral voids on the edges. So, if you can look at it, then this face center, and then the face center on the other atoms around it, they will form a plane, something like this, and these are the 2 atoms. So, octahedral void over here, octahedral void over here, here. So, similarly for all the edge center, you would see one octahedral void. Now, if I were to calculate the number of octahedral void inside this particular cell. So, the ones that are lying on the edges, they are being shared by 4 atoms, which means there are 12 edges. So, 12 by 4 and plus 1 in the center. So, it is equal to 4 in 1 unit cell. So, there are 4 octahedral voids. Okay. So, now let us go to the BCC structure. So, I will take the other atom over here. Now, first let us look at where is the tetrahedral void. So, the first thing that I want to identify is the tetrahedral void. Now, let us look at 1 atom, 2 atom, 3 atom, and then imagine the base BCC, the body centered atom on top of it. Now, this is a straight simple BCC. Here the 2 atoms are not shown different, it is simple as it is, as it should be. So, all the atoms are same color. This is a real BCC. So, this one body centered atom, the 2 corners and 1 over here, these 4 would form the corners of a tetrahedral void. So, we can see 1, 2, 3 and 4. Now, so what do you see here? Where will be the octahedral void? So, if by symmetry you can say this is body centered, this is another center, these 2 are in the plane. So, this should lie somewhere on this surface. So, there will be one on this this side, and another one would lie at here. So, each surface will have 4 atoms, 1, 2, 3, 4 atoms. Now, how many surfaces are there? There are 6 surfaces. So, each of the surfaces have 4. So, we have 6 for the 24. So, let me before we forget, so let me draw this to be able to so let us draw the atoms. These are the corner atoms. And then there is one in the center. Now, let us join this, and like I said, there will be one on the top. So, somewhere over here, not able to show it as properly, and because of this the tetrahedral void would lie over here, over here. Now, there are 4 on the surface, that I hopefully have convinced that there are 4 voids on the surface. Similarly, there will be 4 voids on this surface, 4 voids on this surface. Now, each of these voids are being shared by one more cell over here. So, this belongs to only half of it belongs to this. So, 4 into 6 is the total number, but each of them are being shared by 2. So, 4 by 2, therefore, there are 12 tetrahedral voids. Now, let us go back to our octahedral void. So, these are the tetrahedral void. Now, let us look at octahedral. So, for that again let us come back to our BCC model. So, this is the BCC unit cell. Now, we will concentrate on this body centered atom, these 4 atoms on the corners. So, these 4 atoms on the corners, as you can see, they form a plane, and these 2 corner atoms, sorry, the body centered atoms, they form the atoms which are there along the center axis. So, this is one atom, this is another atom, and one of your octahedral void would lie on this surface. So, this is the total number, this is the octahedral void we are talking about. So, let us draw this part. So, again I will have to draw So, these atoms are also connected with the atom on the body centered of the unit cell on the top. So, there is one over here. So, there is one tetrahedral, sorry, the octahedral void over here. Now, try to identify if there are any more octahedral voids over here. So, can you identify? If you again, either you can look over in the diagram, or let us again come back to this BCC model. So, now what you would see is we were talking about 2 atoms, one above the other, and a plane of atoms. Now, if you look over here, similar kind of structure you have over here. So, this is as well as good as a body centered atom for some other cell. If we had the cell orientation shifted by half x, half y, half z, then this would have become the body centered. So, this itself will become the center line, and this body center plus this body center plus this body center, they will form one plane, and which means that at the edges of these also lies one octahedral void. So, we have octahedral void also at the edges. So, how many do we have over here? We have 6 faces, which means 6 octahedral void because of that, but this is being shared by 2 cells. So, this is 6 by 2 for this unit cell, and we have 12 edges, and on each edges we have one octahedral void, but this one is being shared by 4. So, this is 6 by 2 plus 12 by 4. So, this is equal to 3 plus 3 6. So, we have 6 octahedral octahedral void. So, now we have seen the different kinds of voids in FCC and BCC. However, there is still something that I have not informed you yet, and what you need to see over here is, again I will bring this back to show you. First, let us look at the octahedral void. So, how was the octahedral void over here? As is expected, this is the plane of the atom, this is the other top two atoms. Now, look at the length of the edges, each of the length from here to here or from here to here, or so each of the neighboring atoms, they have same length. But now, let us look at the octahedral void in this one. The length from this atom to this atom, this is how much equal? This is equal to root 3 by 2, and this one is equal to 1. So, the length of these the length here between the different neighbors are different, and therefore, this octahedral void is in fact distorted. So, the voids that we see over here in the BCC, you must remember, are distorted. So, this is a very important aspect that will help us understand the solubility of carbon in two different phases. Octahedral void here are distorted. Now, similarly, let us look at the tetrahedral void. For FCC, you remember this and this plus this, these 4 atoms form the tetrahedral void. Now, you look at the length here to here, here to here and here to here, all of them are exactly same in magnitude. But now, let us come back to the magnitude of length for the different atoms in the tetrahedral void of BCC. So, here to here, here to here, here to here, they are same. But now, what is the length of this one to this one? This is equal to 1 and this one is equal to root 3 by 2. So, this is a different. So, again octahedral, so the tetrahedral voids are also distorted. So, remember that in BCC both the voids are distorted. Now, this is a very important concept. So, before going, let me just summarize what we have looked at. So, we have seen for FCC, let us see tetrahedral, octahedral. Now, for BCC, let us look at tetrahedral and octahedral. So, how many voids per cell we have? We will said with that in FCC 8 tetrahedral void per unit cell and 4 octahedral void per cell. In BCC we saw that we have 12 tetrahedral and 6 octahedral void. How many? Now, we also need to look at void per atom. How many atoms do we have in FCC? In FCC per unit cell has 3 atoms. So, sorry, the 4 atoms. So, that means that for each if we divide by, if we want to get void per atom, then we will have to divide void per cell divided by 4. So, 8 by 4 it becomes 2, 4 by 4 it becomes 1. Now, for BCC there are 2 atoms in 1 unit cell. So, this becomes 12 by 2 6, this becomes 6 by 2 3. So, this has 3 tetrahedral void per atom, 6 tetrahedral void per atom and 3 octahedral void per atom. Now, the other important factor is that if you do a little bit of geometry, not a little bit, but a little bit involved geometry, you would be able to show that R void by R atom ratio are something like this, 0.225. So, it is just 22.5% of the in the radius for what is the radius of the atom. For octahedral it is 0.414. On over here, if you look, tetrahedral voids are larger. So, these are 0.29 and octahedral void are just 0.155. Okay. Now, I will leave you with just one thought. Which one do you think would carbon atom prefer in FCC and which one would it prefer in BCC? So, here what you see is that octahedral voids are larger. So, This means it will be much more easier, less strain, and therefore, you would say octahedral voids would be preferred. In BCC, you would say that here the tetrahedral voids are preferred, should be preferred, because the sizes are larger and therefore, it will be easier or less amount of strain in the lattice. So, you would say this, but then I would say it is not true. What they prefer still is this one. Okay. So, we will extend this understanding in the next lecture, which will help us to understand more about this interstitial kind of impurity. Thanks.